Hello, welcome back to our machine learning course. In the previous lecture, we saw everything about self-attention layers. Now we see how we can use them to build entire transformer models. And the workhorse over this is going to be the transformer block. So, which starts our self-attention layer right here. And our self-attention layers, remember, had this K, Q, and V matrices, so it has some ways to learn. And then we also have a feed-forward block here, which can consist of a number of fully connected layers, typically a simple MLP, which again will have a lot of weights to learn. Okay, we're going to combine that with layer normalization. That's a kind of normalization where every input is normalized independently. Not every batch, but every input. And we're also going to have layer normalization before our feed-forward network. And then we're going to also add a residual connection around our attention block and another residual connection around our feed-forward block. Right? And this will again help us with our gradients, so the gradients can flow through very naturally. Right? So yeah, that's one attention block. So what you can see that this does, first of all, we'll have our sub-attention layer. So this guy will learn how our different tokens will relate to each other, how will influence each other, and then out will come some tokens. And then our feed-forward token will learn some transformation between between tokens we had and the new output tokens, so that we can learn much more complex things. And so that the next sub-attention layer, which will come here, will be dealing with not the same tokens anymore, but transform tokens, and so it can learn even more complex things based on those. Right? And then the transformer model consists basically, there's a few caveats, but basically it's just a stack of transformer blocks. And the deeper we make that stack, the more we can learn and the more data we can handle inside a model. At some point, there's some output layer that we want to do. It could be, in this case, global average pooling, but it could also be a regressive model where we want to pick the next word. Right. Cool. Now, one thing we haven't touched upon yet is that so far these are all set-based models, so the order of the inputs doesn't matter. So if you have a sentence like, the movie was not too terrible, or the terrible was not too movie, we wouldn't be able to distinguish between those sentences. If we want to do that, and of course we want to do that, then we have to add a bit of information to our embeddings. One thing we can do is positional encoding. Positional encoding will basically just directly add a vector to our token vector here. In principle, you could just give a number like 1, 2, 3, and so on, but well, your sub-attention layer will have to deduce the relationship between a 6 and a 3 from this, which may not be so simple. So what people do instead is things like positional encodings like this, where for a certain word, like position, say 1 or 0 here, we're going to take the values of a combination of functions which are increasingly wide, right? So the first one will be very narrow, the blue one here, the yellow one is a bit wider, red one is a bit wider, green one is even more wide. And by doing this, we can make sure that every possible value is going to be different. So there's no, as long as you keep having enough functions that you don't cycle the biggest one, the widest one, you will not have any repetition. They will all be unique. Plus, the very interesting thing is that if we take any other value here, like say at position 17.8, by looking at the relationships between those values and those values, we can deduce how far away we are from any other token in the sequence. And our transformer blocks are going to be able to use that to take into account how far away different input tokens are from each other, and whether they are ahead or behind. They can deduce this from the numbers they get from these functions. Okay, it's a very simple thing to learn, and so very likely our model will pick up on that and will use the order if it's useful. Of course, it's going to be useful to then include the ordering in the calculations and how we want to deal with those vectors. For instance, whether the word not occurs to the left or to the right may actually have importance, right? And so a model will have to learn that using those positional encodings. Okay, one particular class of these guys is autoregressive models. So these are models where that predict the future values based on past values. So if you have a sentence like, well, the move was not 2, then the model has to read the next word, terrible, right? And it will do that by actually giving a possible output probability for every possible word that can come out. It won't do this explicitly. So basically what will happen, there will be an output token, and this output token is then combined with a huge matrix called decoder matrix. And if you combine this token with the decoder matrix, it will give you this whole list of possible words and the probabilities that that's the next word, right? This movie was not too long or terrible or interesting. Those are the most likely next words to occur. Typically, you probably want to have the most common answer, like long, but that tends to create models which are very boring because they will always have the same answer over and over again. So to make it a little bit more interesting, we do kind of we do a temperature softmax, which means that if we have a high temperature, there's a higher possibility that we'll choose a word further down the list, while if you have a very low temperature, then we'll always maybe take the top one. And this gives us some creativity in our model because they will sometimes actually choose very unlikely words. But overall, it will take the most likely words much more often on average. One more thing is that if we want to have an autoregressive model, the tokens can only look backwards, right? So we need to make the transformer causal. And to do that, we can do a simple trick. We can take our weight matrix W, which is the matrix of all the attention values, and we're going to mask out this part of the matrix. We're going to set those two values to minus infinity, so that after softmax, these will all be zeros. And then I solve the whole problem. Now I can have the self-attention layer, which can only look to the tokens to the left, and that's what I want to have an autoregressive model. Okay, let's look at a number of famous transformers. First of all, this is a transformer from the famous paper Attention is All You Need. This was a translation model. So in English you would have a dog on a skateboard, and the output would be something like un chien sur une planche à roulettes. This is an encoder-decoder model. So first of all, it uses transformer blocks to transform the English to a number of intermediate tokens. Then it would use those intermediate tokens as key and values to what's called a source attention layer. And this would combine it with the Q matrix from this master of attention layer. And then from there on, learn how to translate this intermediate representation into French. You will see that typically transformers are either encoder-decoder or entirely encoder or entirely decoder. The most common ones nowadays, like ChatGPT, are purely decoder models. While VIT is typically only encoder models. It's not super important. Yeah, and in some of them, some situations, like I think object detection vision encoders, they still have encoder-decoder architectures as well. Okay. By the way, this seminal paper, Attention All You Need, it didn't invent the self-attention layer. What it did was propose a first model which was entirely based on attention. So it did not have any convolutions or any recurrent neural networks at all. And so this was the first model that used only attention and showed that that's enough for building very capable models. Another very, very famous one is GPT-3. That's the latest one in the GPT family where we actually know the architecture. This is a decoder-only architecture. It has a stack of 68 transformer blocks. Each block has also 96 heads. Secret length of 2000. Input dimensionality of 12,288. So every input token has a length of 12,288. And total has 170 billion parameters. This was trained on the entire Common Crawl dataset in a single epoch, so a single pass through all the text on the internet. And then they did some additional training on high quality data from Wikipedia and other sources. There's an excellent animation by One Blue Tree Brown, so definitely check it out. And also a very nice tutorial by Andrej Karpathy, how to build GPT from scratch. So definitely check that out as well. GPT-4, the latest one, well, now it's 4.0, but it's a very similar architecture. Likely, I say likely because we don't actually know what the true architecture is. We do expect that it's a mixture of experts model. So that's a model which doesn't have pure dense layers, but it actually has sub layers. It has and for instance has maybe 16 it's called expert models. So every of those instead of a normal self-attention layer, it has a switching. So there's a normal self-attention layer, then add a normalize, right? And then the feed-forward part that we introduced here, this feed-forward part, is actually a mixture of experts. It's not one fully connected network, but it's a series of, for instance, 16 of these experts. And here I show only 2 of them. And every expert is trained to be an expert in some part of the input tokens. And there's a router that's a very small model that looks at a token and then decides which of the experts should actually look at that token. Right? And we also train that router on the fly as we train the whole model. So it learns to direct some tokens to some experts, other tokens to other experts. And we typically have 2 of them, which means every token goes to 2 experts. And then we combine the answers of the 2 experts as like a mini ensemble. And that's going to be our output token. The benefit of using these experts is that, well, it's sort of easier to train them continually because you have less chance that you will override information that you learned before, right? Because every expert is really an expert in some part of the token, and it's less likely that we will forget information because it's so focused on some kind of data. At least the chance of forgetting is much lower this way. There's also a big bonus in terms of inference, because if we do inference, and models like ChatGPT have to do a lot of inference, you don't have to push every query through all the layers. You only go to maybe one of the 16 experts, so that makes inference also 16 times faster. Other innovations here are better data. They did a lot more work on cleaning the data, and also a lot of human-in-the-loop training. Right, this is very common for large language models. They seem to do everything by themselves, but there's a lot of human effort into cleaning the data better, doing the post-training fine-tuning with human input. There's a lot of human hand-holding into making sure those models actually are trained well. Okay, this is for now. In the last part, we'll look at vision transformers.